All right, today we are going deep under the hood of a really high-performance reinforcement learning framework. And what's special about it? It's built from the ground up, completely in native C++. It's designed for the vague engine, and it's built to tackle some of the absolute toughest problems in AI. Think robotics, complex game simulations, you name it. Let's dive right in. So right off the bat, the most fundamental choice here is C++ over Python. And this quote just nails why that's so important. You know, in game development, performance is king. Every single millisecond counts. This whole architecture is designed so you can train agents live while the game is running without ever dropping a frame. That is a massive game changer. So what kind of high-stakes problems does this kind of performance actually unlock? Well, we're definitely not talking about simple little grid worlds here. This system is designed for the really complex, demanding stuff, like physics-based robotics and fully automated game testing. And the range of what you can do with this is what's so impressive. We're talking about training agents for really complex physics control, like a bipedal robot figuring out how to walk, or automating QA testing by having an agent explore every single nook and cranny of a level. But, and this is critical, we can also train agents just by letting them watch recordings of human players. Yeah, that last point, learning from recordings, is powered by a technique called conservative Q-learning, or CQL. It's an offline RL algorithm, which means it lets an agent learn from a static, fixed data set. Think sensor data from a real robot or a bunch of gameplay logs. It's designed to be conservative, which is just a fancy way of saying it stops the agent from getting way too confident about actions it's never seen before. And that, right there, is absolutely crucial for safety and stability when you're talking about real-world applications. Okay, so let's get into our first major technical deep dive. How does an agent remember its past when it can't actually see the whole picture at once? This is the huge challenge of dealing with partial information. And this is a classic problem, right? It's technically known as a partially observable Markov decision process, or POMDP. In any realistic 3D world, an agent only sees what's right in front of it. So to make smart decisions, it has to have some kind of memory to build up context. And that's exactly where recurrent neural networks come into play. Now, the two heavy hitters here are LSTMs and GRUs. LSTMs are really powerful, but they're also pretty complex, carrying around two separate state vectors. GRUs, on the other hand, streamline things down to just a single hidden state. And you can see right away, the difference in the memory footprint, just from the component sizes, is pretty significant. And boom, this number just perfectly illustrates that efficiency gain. By simplifying its internal guts, a GRU uses about 25% fewer parameters than a similar LSTM. In a performance-critical engine like this one, cutting down your parameter count means faster training and faster inference, often with basically the same performance. It's a huge engineering win. And here you can see that efficiency in action. On the left, you've got the core math equations that make a GRU cell tick. Those are the gates that control its memory. And then on the right, you can see just how cleanly that translates into the native C++ implementation. This direct, super optimized map from theory to code is what makes real-time performance even possible. Okay, so our agent has memory. Great. But how do we motivate it to actually do anything, especially when the rewards are few and far between? This brings us to our next huge challenge: exploration. I mean, this is the sparse rewards problem in a nutshell, right? If an agent is just wandering around a maze and only gets one little point for finishing, it has almost no information to guide its learning. It's like trying to find a needle in a haystack, completely blindfolded. Most of its actions seem pointless, so the agent really struggles to learn anything useful at all. The solution is just so elegant. We make the agent curious. The Intrinsic Curiosity Module, or ICM, is this little subsystem that basically pays the agent for being surprised. It's always trying to predict what's going to happen next, and whenever its prediction is wrong, it gives itself a small curiosity reward. This pushes the agent to go find new, novel situations that it doesn't understand yet. And the math behind this is actually pretty straightforward. That first formula for the intrinsic reward, it's really just the difference between what the agent thought would happen and what actually happened. So, the bigger the prediction error, the bigger the curiosity reward. And as the whole system learns to get better at predicting, it naturally drives the agent to explore every corner of its world. So we have an agent with memory, and it's curious. Now, how do we actually train these complex recurrent models efficiently, especially when we're dealing with long gameplay sequences? Let's look at the engine of learning. Well, If you have an agent that plays for thousands of steps, trying to backpropagate an error signal all the way back to the very beginning is, well, it's pretty much computationally impossible. The gradients just vanish or explode, and the memory you'd need is just enormous. The solution is something called truncated backpropagation through time, or TBPT. Instead of trying to process the entire episode at once, we chop it up into manageable chunks. For each chunk, we do a quick burn-in to get the agent's memory up to speed. Then, and this is the key, we detach the state, which stops the gradient from flowing backward, and we only train on the second part of the chunk. This whole process makes training on super long sequences both stable and totally manageable. Of course, even with a clever trick like TBPT, this is still a ton of computation, and that's where this native C++ architecture really gets to shine. The entire training pipeline, from matrix multiplications to activation functions, all of it is executed directly on the GPU using custom-written Vulkan Compute shaders. And the performance impact is just staggering. By writing custom GPU kernels that are perfectly tailored for these neural network operations, the system can get training speedups of up to 100 times compared to a CPU-based setup. This is what makes real-time training and rapid iteration actually possible. Okay, so finally, let's zoom out a bit. All of these individual technologies, the GRUs, the ICM, TBPT, they're all possible because of a core foundational philosophy, a blueprint for how to build these kinds of high-performance AI systems. And these are the 4 pillars of that philosophy. You've got pure C++ for raw speed, a pure entity component system, or ECS architecture, for super flexible, data-oriented design, native GPU performance through Vulkan for all that horsepower, and finally, being deterministic by default, which means you get bit-exact reproducible results, which is a lifesaver for debugging and research. So the big takeaway here is that this isn't just a collection of algorithms bolted onto an engine. It's a cohesive, deeply integrated system where every single piece, from the data layout of an agent component all the way down to the Vulkan kernels, is designed with just one goal in mind: maximum performance for creating truly intelligent agents. And that really brings us to a final thought. When you completely remove the performance bottlenecks that have traditionally held back AI, what new possibilities open up? What kind of complex, adaptive, and truly intelligent behaviors become possible when the only limit is really just your imagination? Thanks for tuning in.